Okay, hello, my name is David Scher. I'm here for Physics 572, Introduction to Health Physics. We are moving on to our ninth unit in the course. This is related to radiation detection and measurement. And so I'm going to start off by asking if anybody has any questions for anything up to this point in the class. Okay, hearing nothing, I'm going to go ahead and move ahead. I do owe you some homework grades. I have done the problems, and I will post those so that you can look at how I approach the problems and compare them. And as soon as I can, I'm going to get these turned around for you so you can have some feedback on what you did so far. Okay, so for today, we are going to look at my screen related to radiation detection. So we have two, as usual, we have two portions to this divided somewhere around 7 p.m. maybe. And the first will be related to how radiation detection instruments work. The second portion will be about how we use those instruments to make measurements, how we figure out activity or other measurements based on using those equipment. Okay, first thing is first of the basic idea is what is it that we are what do we use the radiation instruments for? What are we measuring? Well, in some cases, we're doing very qualitative measurements with the instruments. Just simply, is radiation there or not? And sometimes it's more quantitative. Some of the things we measure with some of the quantities we measure when we do quantitative measurements are the flux, the number of particles per square centimeter per second, or the fluence, just the number of particles per square centimeter. We covered that before. Those quantities, those concepts, when we talked about external dosimetry. We use instruments to measure the dose, the energy that's deposited per gram. We've done a lot of calculations, or a number of calculations, calculating air kerma in our work up to this point. And in some cases, we measure the dose equivalent. That includes a factor for the amount of damage done by radiation. The instruments we talk about today don't include that, but some instruments for measuring neutrons, for example, read out with what is essentially the dose equivalent and not just the absorbed dose. Okay. Most of what we've been talking about in this class relates to photons, X-rays, gamma rays, that sort of thing, and beta particles. In those cases, the radiation weighting factor is 1, so it's not relevant. But with heavy charged particles or heavy, even uncharged neutrons, the radiation weighting factor can make a significant difference. Our measurements can tell us about the type of radiation. We have to consider whether we're dealing with alpha particles, neutrons, beta particles, X-rays, etc. And we have instruments that can distinguish between them. So there are many other quantities that are of interest. The energy of the radiation, it can be measured as a function of time. We can log the data we're measuring, etc. So there can be many different things that we're measuring. Now, one thing I'd like to point out is that it's not possible we don't measure the radiation itself. Even with charged particles, we don't measure the charged particle itself. Instead, we have to convert the energy into something that can be detected, measured, and quantified with instruments. And so we need to amplify the energy that's deposited into some kind of electrical signal. So we use the physics that we've learned about how radiation interacts with matter to convert one single electron or one single photon at high energy into, it will liberate electrons that create a large number of electrons, and that's something our instruments can measure. So there's some amplification of the charge into some electric signal. And so it's, in a way, it's kind of indirect, but it's based on all the physics we've learned about how radiation interacts with matter. Okay. This is true whether it's alpha particles or electrons or photons or anything. For all these different kinds of radiation, we have to convert them into a charge that can be detected with electronic equipment. So when we're working with radiation detectors, basically what we're how it's working, how a radiation detector operates is that it lets the radiation that we're measuring ionizes something in the detector, and then we measure the signal from that. Okay. And we're going to talk about different kinds of detectors: gas-filled detectors, scintillation detectors, solid-state detectors, but in each case, it's this secondary phenomenon that we're working with, that's just a conceptual thing that helps us set the frame for what we're going to talk about. So what we would like to have in a detector, we'd like to have to be very efficient. We would like to have a high probability that if radiation is present, that it's going to be measured. We'd like it to produce a big electrical signal, so we want to convert the photon energy, the radiant energy into some macroscopic electric signal. For gas-filled detectors, then that means we need to consider what the number of ion pairs produced per electron volt, or the electron volts, how much energy it takes to produce an ion pair, for example. We have to make sure that the electrons, once they're liberated, once the ionization takes place, that they don't recombine, that they are efficiently collected by the radiation detector. And so our design has to address that concern. Now, the charges that are being liberated are very small. It says in the slide, 10 to the minus 13 coulombs. And so we have to have some kind of amplification that takes place. In some cases that's done, or with gas-filled detector, that's done with a capacitor. The capacitance of a capacitor is an object that when charge is present, it produces a voltage. The voltage is proportional to the charge that's deposited divided by a property of the device called the capacitance. Okay, so the types of detectors we'll have gas-filled detectors. These can be ionization chambers, proportional counters, or Geiger counters. Scintillation detectors. In scintillation detectors, the radiation produces a flash of light when it's absorbed in the solid state device or the liquid device, and those flashes of light are then collected and counted to create a signal. So scintillating means giving off little flashes of light. If someone says you're a scintillating conversationalist, that means you're sparkling, you're brilliant. The other kind that's common is semiconductor detectors, where semiconductor materials like either silicon or germanium are used to detect radiation. It creates ionization in this crystal, creates an electron hole pair, and then the energy that's deposited gets measured by the electronics that collects these. And we'll see about the advantages of each, I think, later. So we're going to divide the world into two parts. We're going to talk a lot about gas-filled detectors. They're sort of the workhorse instruments. in most cases. We'll talk a little bit about solid state detectors, either the scintillating kind or the semiconductor detectors I just mentioned. Gas field detectors are the most common type. They're relatively simple construction. They have a wire or some kind of electrode suspended in a gas-filled volume. They can be made into very large volumes, and they're very easy to use. They're either used for counting purposes, so to see how many events are taking place, how many decays are taking place. And that's one form of this. We're going to talk about proportional counters. And they can give us information about how much energy is being liberated, how much energy the radiation has. So they're typically filled with inert gases, either noble gases. Often they're noble gases. There are some other gases that are incorporated. We'll talk about it. There are free air ionization chambers as well. They have a low detection efficiency because it's just a gas. Remember we talked about the mu over rho is a constant over a wide range of energies. Well, when rho is very low, then mu is very, then we don't have as much mass to absorb the radiation. So particularly for low energy photons, the gas field detectors are not very good. They're better for charged particles. Okay. So here are some ideal properties if we're trying to design radiation detectors. For alpha particles, we want to have a very thin or no window. That's because alpha particles have a very short range. So we're going to have a gas-filled volume or some sensitive volume. We don't want to have a very thick window that the alpha particles need to pass through to be detected. For beta particles, we need a relatively thin window, particularly for low energy betas. But for higher energy betas, it's not as big an issue. For photons, we want to have a high density. So scintillation crystals, solid state detectors are more useful for photons because they have more dense material to interact with. We'd like to have a high atomic number for photons. For neutrons, we want a low atomic number material, particularly those with lots of hydrogen are beneficial. It helps thermalize and capture the neutrons. Okay, here are some examples of gas-filled detectors. On the top, we have of the picture, we have ionization chambers. We're going to spend a lot of time looking at those. The one that's at the very top of this picture looks like a cutie pie, is an old name for a particular model. It had to do with Q for charge, T for time, and so that's why it was called a cutie pie, not just because it was good looking. This is on the left side, you see a proportional counter. On the right side, you see a couple of Geiger counter type detectors. For gas field detectors, noble gases are a good choice for filling the material or for filling the gas filled chambers because they have they're relatively easy to ionize. They don't take that much energy to ionize compared to some other forms, other gases. They're very mobile, and so that the electron that's liberated is obviously going to be mobile no matter what, but you want the ion that's left behind to also be able to neutralize so it can become sensitive again. And monatomic noble gases are good in that regard. It's pretty easy for them to move around to be neutralized on the perimeter of the anode of the device. Let's see. Noble gases are not electronegative, so they won't recombine with the electrons very readily, and so they're very make it more efficient for collecting a signal. Here's an illustration on the top of a sort of a ideographic picture of a gas flow detector. So as radiation passes through the sensitive volume with the gas, it ionizes the gas. Some ions, there are electrons that are released, and then the remaining ions are left. We have an electric field across the device. So there's some negatively charged plate or electrode and a positively charged electrodes. The electrons move toward the positive, the negative of the atoms, the ions that were created move toward the negative charge anode. And so we can collect a signal, usually from the electrons. They move much more rapidly. The value of energy required per ion pair for different kinds of materials are shown here. And so they're relatively high. Let's see. So that makes for a good choice of material. And they also have a difference between electrons and alpha particles, so that makes it the ability to discriminate between the two possible. So here's another illustration. When these the number of incident particles is low, let me go back to this. When the number of incident particles is low, we can allow these electrons and ions to drift or to move in the volume and count individual events. So if it takes if there are not an overwhelming number of radiation particles passing through, we can clear out an event before another radiation particle comes through, and so we can count individual photons or electrons, and that can be used then to measure, to infer how much radioactivity is present, what the emission rate is. When it's a very high rate of many photons or many electrons or many radiation particles passing through, we can't discriminate individual events, and in that case, we look at the overall amount of energy deposited and get a measure of the radiation field. We're not counting how many particles have passed through. Instead, we're measuring the intensity of the radiation field that's present. Is this distinction clear? Okay. Okay. So if we have a detector that's like this with a voltage applied across a gas, we can apply different levels of voltage to it, right? We could have it operate at a few volts up to 1,000 volts or more. 1,000 is about the limit. So as we apply different amounts of voltage, we have different properties that take place, and that's what leads to the different kinds of detectors I've been talking about. At the very low voltage levels, there's not enough energy to pull the electron and the ion apart. Remember, the ion is positively charged, the electron is liberated is negatively charged. There's a force attracting them back together. And so they can recombine unless there's an external electric force that pulls them apart more strongly than that. So the low voltage, when we have a small voltage applied across the plates, then that's the region of recombination, and it's not good for radiation detection. So far, so good. If we go to a higher voltage, then we have sufficient voltage to separate the ion and the electron and be able to collect the electrons and ions. Right. And so that's the ionization region. The ionization chambers are operated in that region where there's sort of a flat plateau of response with different applied voltages. As we go to higher voltage, there's more and more electrons collected compared to the voltage before. So what's happening here is there's more voltage. The electrons that are liberated are moving at a higher rate of speed, and they can collide with other gas atoms and liberate electrons. Then you can have sort of an amplification, because one electron that's liberated is accelerated so high it can so quickly it can create more electrons, and they can interact with other gas atoms and produce more electrons. So as you go to higher and higher voltage, you get more and more signal. Okay. Beyond that, there's what's called the region of limited proportionality, and it's the same phenomena are taking place, but it's occurring in a way that creates confusion. It's harder to interpret the results in the region of limited proportionality. And I'll explain what's going on the other side of it and explain why. So when we go to very high energies, then we have this sort of multiplication that takes place. But there's the electrons that are liberated get enough kinetic energy that's accelerated so much that they can ionize gas, just like I mentioned. But there's so much of that going on that the entire volume of the chamber is ionized. And that's what we operate at the Geiger region. And so each event that comes in gives us a complete signal, whether it's a very low energy photon or a very high energy alpha particle, it gives us the same signal because all of the ions in the chamber are being ionized. Okay, so it gives us the same output electrical signal. In the proportional region, then the energy of the photon or radiation that's incident on the detector will be proportional to the strength of the electric signal, the number of ion pairs collected. The amplification will be proportional to how much energy was deposited in the detector. In the region of limited proportionality, we have a little bit of both going on, so it's harder to interpret. So the three regions that are useful for radiation detection are the ionization chamber region, it's shown here B, proportional region, region C, and then the Geiger region, region E. At the very end, region F, at very, very high voltages, above 1,000 volts or so, an ionization event can cause continuous discharge, and it just doesn't work as a detector anymore. Okay. Let's see. So I've gone through these already, so we'll talk about it a little bit. The parts that are not useful are the region, combination region, and limited proportionality, because the signal isn't as useful for us for interpretation. Now, in the ionization region, the amount of energy that's being deposited in the detector is proportional to the energy of the radiation that's incident on it. And small changes in voltage don't have a big change in the signal. And so it's very robust and it's reliable. It's good for field instruments that might be subjected to difficult environments and not be handled very carefully. And so that's why ionization chambers are some of the attributes of ionization chambers that make them useful. Proportional region, these instruments are usually more related to laboratory type equipment, where you can have a more controlled environment. There are some field proportional counters, and we'll show examples of them later, but they're not as robust. They're more sensitive than ionization chambers. They're useful for counting activity and for discriminating different kinds of radiation. The different radiation energy that's deposited by a low energy photon is different than the energy deposited by a high energy photon, and you can see that in terms of the pulse height that's produced. The signal that's produced will be different for a low energy or a high energy radiation. Geiger counters are useful for they're very rugged, very robust. Again, it's flat with voltage, so it's very good for field operations. is useful for looking for contamination in particular, and not so much for measuring dose rate. Okay. Let's see. In the ionization chamber region, so the number of we typically collect the electrons, and that's what the signal that we're measuring is proportional to the energy that's deposited along the path through the device. And so high energy photons will have a number of or high energy electrons, for example, will have a number of ionization events and deposit more energy than low energy photons will. And so that's what is shown on this graph. The curve A is for high energy beta particles depositing more energy, so they give more signal. The pink curve B is for a lower energy beta particle, about 0.1 MeV, and so they give less signal as they pass through. Okay. When we're operating with an ionization chamber, it's possible to use them in a count rate sense. If there's a very low signal or low number of photons that are incident on it, it can count individual pulses. It's not very efficient in that case. So usually ionization chambers are operated to collect current over a period of time, or to collect to measure to collect charge over a period of time and get a cumulative amount of ionization to take place, or to measure current, the rate at which the electrons are being liberated. So those are the two ways it can operate. And usually it's not measuring individual events. That's not the way they're normally operated. This is in the ionization region. This is an example of what an ionization chamber might look like. There's a case to control the environment. Then there will be 2 electrodes, one for positive, one for negative. And there will be by applying a voltage across those 2 electrodes, we create an electric field. Okay, it's a relatively low electric field, and so the only thing we're collecting are the ions that are liberated by the radiation itself. There isn't multiplication taking place in the gas. It's not, the electrons are not being accelerated enough that they can cause an avalanche. So the signal for individual events are very small. Instead, we're measuring that the total number of photons that might pass through this, or of charged particles that might pass through this per unit time. It's not very good for energy resolution. It can't tell much the difference of the energy of the primary radiation, just the overall energy that's being absorbed in the chamber. Now, for in a pulse mode, for example, with proportional counter, it's possible. Well, let me look for the picture. So we have ionization that's taking place, and then this is going to be neutralized over time, and so as these electrons or the ions are neutralized, the charge will drop back to 0. And that's got to do with the design of the system. There's an RC circuit that does that. So it's possible to have a very small, a very rapid time constant. The signal returns to normal very rapidly, or it can have a longer time constant. And that's got to do with the design of the system. Let's see. And so that you can have either of these properties in a radiation detector. This figure actually comes from Staben's book that you have, and I think it's just showing that there are differences between different styles, and that's something to think about when you're interpreting results. When ion chambers are operated in pulse mode, not a very common application. Then when events take place, the current that's produced is decayed away, and discrete measurements can be measured. The amount of charge is liberated is the pulse height. That's how strong the signal is. And so there are devices called single channel analyzers that ignore some pulses that are low, that might be below some threshold, and count those that are above the threshold. Okay, we'll talk more about the electronics at the end. But if there are a lot of background radiation that's low intensity, and then you're measuring events that occur that are a higher intensity, you can distinguish between the two in an ionization chamber or a proportional counter. Ionization chambers can be used for measuring radioactivity, particularly when there's a large amount. This is a dose calibrator that's used in nuclear medicine. It doesn't count individual events. Instead, it figures out what the activity of the source is based on the exposure rate. So it's measuring the ionization that's taking place in the cylinder. The radioactive material is put in the middle of the cylinder, and in the walls around it, the amount of ionization that takes place is proportional to the activity that's present. The nice thing about it is that because you're measuring things on a continuous basis in terms of current that's produced, there is no dead time. We don't have individual pulses that might trail off slowly and paralyze the device. So that's one use of an ionization chamber for measuring activity. Here's a schematic of the ionization chamber that we talked about before. There are two electrodes. There's an enclosure that holds the gas. A voltage is applied, and a measure of the current that passes through is a measure of the radiation, the amount of radiation in the area, radiation field. In an ionization, each ionization event requires about 20 electron volts, 25 electron volts, depending on the gas. So that means for a 5 keV electron, it'll produce only 200 ions. For a 5 MeV alpha particle, it'll produce 200,000 electrons, so that you can see the signal will be different between those two. Okay, so there's a bias voltage, that's the accelerating voltage that allows us to collect it. Then that voltage produces an electric field, which causes the charges to move toward each electrode. The speed depends on how big this bias voltage is. If we have a large voltage, the electrons move more rapidly, and that's why you might get a multiplication at higher voltages, but not in an ionization. So if we look at the total amount of charge, if we look at the ion, what's going on inside the detector, the ions are traveling relatively slowly, so they take longer to clear out. The electrons are relatively quick. They clear out much quicker. And so the charge that's being collected at the electrodes increases in this way. The current is shown here. And that's why you have these tails that I was telling you about. Let's see. When you're operating current mode, we don't worry about the pulse. We don't worry about the tails. It's continuous operation. Ionization is taking place all the time because radiation is producing or passing through it all the time. And so the signal, the amount of current that's produced, is proportional to the amount of radiation that's passing through. And so it's a good measure of the dose rate because of that. Okay. In the proportional region, then gas flow detectors can be used for measuring radiation, and they're sensitive to the energy that's deposited per event, as well as the count rate. The amplification that takes place, as I said, there's a cascading that takes place because you're at a higher voltage of a cascade of ionization, or an avalanche of ionization. leads to an amplification of about 1,000 or 10,000. And so that makes the signal large enough to be countable. Proportional counters are more sensitive than ionization chambers because of the amplification that takes place. They're useful for low field intensities because they're more sensitive than ionization chambers are. Here's an example of in a proportional counter. Now, in a cylindrical detector, well, doesn't matter. The electric field is such that because the electric field is around these electrodes, the electric field is higher near the anode than throughout the volume. So most of the amplification takes place around that electrode. This is for like a cylindrical geometry. And so in a proportional counter, the electrode, this amplification because of this avalanche is taking place near the electrode. In a Geiger counter, it's going to be something different, and so we'll see that. And so you can see that the signal is going to be the amount of amplification is going to be the same no matter where the event takes place, you can still be able to, even with the amplification, you're able to detect individual events in a proportional counter. Okay, now this amplification process, it looks pretty uniform here, but there's variation of and more variation is introduced because there's some fluctuation that takes place in this amplification process. Sometimes there's more charge produced, sometimes less. There's an average that you would see, but you'd see some variation, some dispersion. So this is an example of a proportional counter, a central wire with the anode, cathode, anode around the outside. You have a high electric field near the center. The electric field goes as 1/R. That's why all the avalanche takes place near the electrode. Let's see. We have ionization that takes place, which gives rise to amplification. It can be used to detect all kinds of radiation, not just photons. It can detect beta particles or electrons, can detect alpha particles, can detect neutrons. Generally, the gas that's used for this is a noble gas, such as argon, because they have they allow the most amplification. Let's see, so they can achieve gains of 1,000 to 10,000, as I said already. Now, it's possible, it's not that uncommon that what you'll have is this chain reaction of the avalanche is self-sustaining, so it can cause further ionization events that like what I described in the breakdown region. We can solve that problem, and what this occurs because when the ions reach the metal at the anode at the outside of the detector, they can when they recombine there, they can give off UV light, and that can cause another avalanche. And so if we put in a gas that absorbs UV light, and there's some examples shown here, they absorb that UV light, they can quench that reaction, and so you don't have this parallelization problem. A common gas that's used is P10 gas, 90% argon and 10% methane or isobutane. Okay, these are the geometries for some proportional counters that are used in the field. This detector, the flat one, is used for measuring surfaces. The others are for can be used for measuring radiation areas. Has anybody used these devices as gas flow detectors? Okay. Let's talk about Geiger counters then. That's up in the high voltage region from, I don't know, 800 volts to 1,000 volts, something like that. In this case, there's enough acceleration so that the electrons that are liberated ionize more gas molecules, and those electrons ionize more gas molecules, and the entire chamber ends up being ionized. So you have one signal that's the same size signal no matter what caused it. That's why you have the same click, click, click. You have the same signal from everything. The amplification could be 10 to the 9th or 10 to the 10th because the entire volume is being ionized. They're not good for measuring the energy of the radiation that they're detecting, but they're good for indicating the presence of radiation and usually used for safety surveys and that sort of thing. The disadvantages, they suffer from long dead times because the entire volume is being ionized. It takes a while, longer than for other counters, for them to be neutralized and ready to detect again. In some cases, they can become paralyzed because this ionization phenomenon, this avalanche can cause secondary signals, and the entire volume can stay paralyzed or stay ionized in very high radiation fields and never come back to neutral. And so they can be very give a false sense that there's no radiation. It can't detect radiation at very high levels, and that can be misleading. And so they should not be used in high radiation areas. This is a summary of what we've just talked about. It'll be good for you in your notes. So we have these avalanche taking place. And so again, Geiger counters operate in this region 5 on this chart, around 1,000 volts, depending on the geometry. They need a large voltage. They have a lot of amplification takes place. They have a Geiger gas, and which includes some quenching gas, and the signal is the same no matter what energy is being deposited in the detector, but it's the most common form. This is a sausage type detector. It's very old. I think I might have one of them here. This shows a picture of the spread of an avalanche from Geiger counters, and you can see that one event can liberate electrons that cause other avalanches away from the event, and that's why the entire chamber gets ionized. Okay, is this all clear? Okay. Here's a schematic showing it. We have a window that allows the radiation, particularly charged particle radiation, to enter. We have our anode that collects the electrons. We have our cathode that collects electrons. We have a voltage that's applied to that chamber relative to the central wire, and we get a signal out. The capacitor here allows first of all, it does two things. The preamp, it matches the impedance so the signal isn't lost, and allows for the charge to be dissipated and returned to normal. Here's an example of what's called a pancake probe. Because of the geometry of it, it has a large surface area. It's used for scanning areas for looking for contamination. It operates again in the Geiger-Müller region. These are both pancake probes. This has got a sausage probe that can be swapped out, used for different applications. This is like a personal alarming dosimeter on the right that can be used, usually operate with Geiger counters, can be used to tell radiation levels that an individual is exposed to, for example, in emergency situations. Okay, what are the differences between a proportional counter and an ionization chamber? Let's compare the two. They both are gas-filled detectors. Both can count individual events or steady current to measure the radiation field. The proportional counter is the output is proportional to the detector voltage. An ionization chamber operates at a plateau. Its output doesn't vary much with any variation in voltage. The proportional counter can produce pulses that are proportional to the incident radiation's energy, and so they can distinguish between types of radiation. You can tell a high energy photon or high energy beta particle from a low energy photon or beta particle. Proportional counter versus GM. The GM counter work at very high voltage. They completely discharge the gas in the tube. And so they have individual counts that are not proportional to the energy of the radiation. They're very rugged. They're very inexpensive. They're easy to use, very common. Proportional counters are much more sensitive and used in particular applications. Let's see. Another kind of detector, this is a semiconductor detector. In a semiconductor detector is a solid. In solids, remember we talked before about there are energy levels in individual atoms. When many atoms come together to make a solid, all those energy levels are overlap with each other, and so we get bands of energy that are possible. And then there are bands that are where the electrons cannot have certain energies. And so when a photon or any radiation causes ionization, the electron is moved into a conduction band where the electron can move around through the solid. The hole is left behind that's limited and can't move as rapidly. And so this process allows us to collect the charge that's proportional to the radiation that caused the incident ionization. They're very sensitive. They're very good at detecting or discriminating the energy of the radiation that's being produced. Is very much less variation. We talked about all of the fluctuations that take place with amplifications in a gas. There's much less fluctuation that takes place in a solid state detector. Another kind of solid state detector is called a scintillation detector. The way it works is a high energy photon will interact with the detection instrument, the volume. An instrument, some volume is contained, has some solid like sodium iodide, will absorb the photon and create a flash of light of several photons of visible light that's proportional to the amount of energy that it received. Those photons of light are then interact with a photocathode. This is so basically using the photoelectric effect we talked about very early. When these photons of visible light interact with this material, that material releases electrons. Those electrons are then accelerated toward this detection device. Is called a photomultiplier tube. In these photomultiplier tubes, there are stages that are called dinodes. When one photoelectron interacts with it, there'll be some there's a high voltage that attracts the electron. When it interacts with that dynode, it will liberate more electrons, a few hundred or thousand. They'll be transferred to another similar dynode that's at a higher voltage. For each electron that's reaches that point, that same number of amplification will take place, and so it'll go through several stages, and the number of electrons will be multiplying each time, and so we get a large signal on the outside output. So instead of amplification taking place in the detector itself, where the sensitive volume, where the gas was, instead the amplification takes place in the photomultiplier tube electronically. They're very good at discriminating different energies, but they have some variation in the amplification that takes place at each stage, and so you have a wider dispersion of energy on the output side. Okay, so far so good. Need more clarification? Okay, and so this is a narrative that describes what I just told you. with the diodes and the amplification that takes place. So we have our output either from a scintillation crystal or from a proportional counter. The output of that is some electrical signal that's been amplified either in the gas or through the diodes in the photomultiplier tube. That signal, that electrical signal, goes to an amplifier. The amplifier is then can be sent to an analog to digital converter, so that the height of that signal, the voltage height of that signal, can then be digitized, and we can get a record of the how many, the different distribution of pulse heights coming out of the detector. This can then be used to infer information about the radiation, what the energy of the radiation was, how many there were at each radiation level. This is a device, it's called a multi-channel analyzer. It's so it logs the different signals, the number of events that take place with different voltage heights, and so that's how we can get the data as a result. Let's see. Okay, so the output of a multi-channel analyzer hooked up to a sodium iodide crystal might look like this. The energy, the pulse height is on the bottom scale, and the number of counts in that with that pulse height is on the y-axis, the vertical scale. And so we can calibrate. Now, the amount of energy that's released from the crystal and ends up as a signal is proportional to the energy that was deposited. And so there is a certain signal here that if it's in this case, the signal was can be calibrated to cesium-130. We use cesium-137 to expose it, so we know where that pulse height is, where the photoelectric peak is. That corresponds to the energy of a cesium-137 gamma ray, which is 662 keV. These other features that we have here are related to things we talked about before. This is the Compton edge, where the Compton, so in that scintillation crystal, Compton scattering is taking place. So some of the energy that's being absorbed is due to Compton scattering. That's what all of these counts are here. This is the photo peak where there's a photoelectric effect taking place. So it's the full energy of the radiation. And this is all due to background counts, etc., from some other source. Okay. Okay. So why do we use different detectors for different purposes? What do we use gas flow detectors for? We use them because they're inexpensive. The sodium iodide crystals are much more expensive, relatively speaking, or semiconductor detectors are much more expensive. They're relatively inexpensive. They're relatively rugged. They're useful for measuring radiation fields, and proportional counters are useful for measuring individual events and counting the type of radioactivity that you might want to measure the activity of. Semiconductor detectors have much better energy resolution. They get more charge, better signal from individual events, get a better signal to noise ratio. They're very high density, and so they can be very effective for measuring photons. They have a higher probability of capturing a photon, higher efficiency for counting, and they can get very high, very good energy resolution. I think I already mentioned. Scintillation crystals are more inexpensive than semiconductor detectors. They can be made to be very large. So in nuclear medicine, they use single scintillation crystals that may be a centimeter in height and maybe I don't know, 30 centimeters in diameter. Well, more than that, maybe a meter in diameter. So they can be very large crystals. let's see, you get a very large signal depending on the photomultiplier tube you use a sophisticated photomultiplier tube, then you can get a good signal out of them. So they're very readily detectable. The sodium iodide is a very common one. It's been around for a very long time. There are other materials, bismuth, germanate, and other materials that can also, and plastics can produce this effect as well with scintillation. I want to mention something about geometry. So when you're measuring sources, measuring radiation sources, if you're in many cases, the source will be external to the detector, and so the amount of radiation, the fraction of the solid angle that's subtended, that's absorbed by the detector, will be a small fraction of all the radiation eliminated. This is very similar to that flux and fluence we talked about a while ago. The radiation is traveling in all directions, but you're only detecting a small portion of it. And so the solid angle that's detected is given by the formula at the right. And for the distance d and a radius of detector r, that's what the solid angle is. The fraction that you're collecting is only that solid angle that's shown by this formula divided by 4 pi. That's the total solid angle. And so you have to be aware that you may not be, that your measurement may not, needs to be scaled up to reflect that. So this is another illustration of the same concept, that the solid angle is related to the distance squared and the radius of the device being captured. So this is an illustration or an example problem of figuring out what portion of the solid angle is being captured by a detector. It has a radius of 10 centimeters, and you're at a distance of 20 centimeters away. So you want to calculate the solid angle that's subtended by that. We use this formula here. It's the distance divided by the sum of the distances squared and the square root of that. And so we put those numbers in, and it turns out that we have a solid angle that is about 5%. So about 5% of all the events that are taking place will be intercepted by our detector. Then there's inefficiencies that we'll talk about later that take place inside it. So you can improve your efficiency by being very close to the event. So when you're using a Geiger counter to do frisking, the technique that I've always advocated or told is you want to have your pancake probe, if you're using that, about 1 centimeter away from the surface that you're detecting, so that you have a good solid angle, and you want to move it at a rate of about 1 centimeter per second as you survey the area. Okay, that's everything I have for the first video. I'm going to give you this, well, you've already got the link to the second video, but I'm going to start the second video now so we can go on. The second video is going to be about counting and how we can use these detectors to quantify the amount of radioactivity. So let's give it 5 or 6 minutes so people can have a breather, and then, or 5 minutes, and then we'll start again, okay? Questions or objections? Okay, I'll see you back shortly.